So earlier we have looked at the two different methods of formula when it comes to solving surface integral, right? So now we're going to look at getting surface integral for scalar field. Alright, but see to that it's kind of more or less the same. So if you're given a z in terms of a function of x and y, alright, and then your x and y will be the element of your d. If you remember, d is the shadow of the surface object that you actually get. So if you remember method 1 earlier in the first part of the video, we'll have your s, which is, so this is for scalar field, yeah? So when it comes to scalar field, you will see that we will have a vector field here, and in this case I will have g, function of g, y, and see that I am going to plug in my z instead of z here. I'm just going to replace it with my f of xy. Alright, and if you can guess the remaining one, just like what you looked at earlier in the first part, alright, so you will see a square root, alright, in which this square root, I'm just going to write it down over here. So my square root will be, again as usual, my 1 plus df over dx square plus df over dy square, given by, again, dA. Alright, so see to that for method 1, so this is more or less the same like what you saw as the basis here. So see that this is actually combined together, but I don't have any space, so this one is actually this one here. Alright, so that would be for scalar field. So see to that it's actually kind of the same, especially this term here, but you only add the first term here, which is the function. So how do we know of this function? It really depends on what the question asks you. They usually will give you the expression. So you just make sure that in the expression itself, you would not have a function of more than 2 variables. In this case, if you want to say, because method 1 is usually used for Cartesian plane, right, if you remember. So in assuming that for this formula, we are looking at surface object on xy plane, and you actually have a vector with the expression of x, y, and z. So you just make sure that you just rearrange your z to be expressed in terms of a function of x and y. Alright, so that would be it for method 1. And for method 2, as what you can remember clearly, that would be for my parameterization, isn't it? Usually used for my cylindrical object or my spherical object. So in this case then, alright, so my surface integral of my f x y z ds, alright, will then be equivalent to, so see to that this one also applies to this, alright, where you are given a function of x, y, and z. Because but over here we're talking about scalar field. So again, since we have parameterization, remember earlier we actually use and express it in terms of u and v. This is just generalized version of it. If you remember earlier, usually we deal with either phi or theta, depending on what the shape is. So by now you will know that you just see an addition of first term here. Second term still remains the same as what you got earlier. If you remember, this would be your r of u. So see that this one would be actually a differentiation of your r with respect to u. Yeah, that's why the small subscript over here. And you get, what you do is that you get a cross product indicated by this first vertical line, and then you get the magnitude of it. So, and again, this is dA. All right. So of course you're going to look at examples and all that as you go on with trying out more examples, you will be able to see the difference. All right, but if you master the first part earlier, this should just be more or less the same, only that you have an additional one term here. All right, so this is method 1 and this is method 2, and that would be for surface integral for scalar field. All right, in the next video we're going to look at surface integral for vector field. But of course, for vector field, earlier I mentioned that we actually need to know a little bit on unit vector normal, so I'm going to explain that in the same video as well. All right.